We left off in our notes talking about the heat of combustion and the heat of formation, so we're just going to review and make sure that we have these definitions down on this sheet so that we can practice Hess's law, calculating it both what I call the easy way and then what I call like the short way, which is the easy way, and then what I call the long way, which is a little bit more difficult, but it helps us understand exactly how the final equation is being found. So we know that the heat of formation is the energy change when a compound forms from its elements, and that symbol is a delta, capital H, with a subscript F. So the more negative the change in H, the more stable the substance. The heat of combustion, then, is the energy released when 1 mole of fuel burns, and that symbol is a delta H and then COMB as the subscript. So, for example, the combustion of propane releases 2,219 kilojoules per mole. So this should be a review from the slide of notes, but I just like to have us write it down again for repetition, as well as to have those definitions on hand while we practice calculating Hess's law. So again, Hess's law is the overall enthalpy change in a reaction, and it's equal to the sum of the enthalpy changes for the individual steps in the process. So I'm going to teach you how to calculate it the long way first, and then you know how to calculate it the short way because that's what we did on the notes, so then I'll just reiterate how we can do that. So the long version, to calculate the change in H for the combustion of methane that produces water, is we'll have to have our parent equation, if you will, which is the actual combustion of methane, and then we're going to organize our data. So we've got our substances here, and we're going to identify the number of moles in the compound based on the coefficient, and then what we're going to do is figure out our change in H values, our change in heat of formation values from our blue sheet. So we know that CH4 is a negative 75, oxygen is 0 because all elements by themselves are always 0. Carbon dioxide is negative 393.5, and then liquid water is negative 286.0. So we've identified our heat of formation values. So then what we're going to do is write out the equation for the formation of each substance. Now, when I do Hess's law the long way, I will give you those 3 equations, and I will give you the parent equation. I never expect for you to write out the equations for the formation of each substance. I will give you these. You will also get these values. We might need to do some manipulation with those values. So here are our equations for the formation of each substance. So then what we do is we rewrite the equation in a way that when added together, they will cancel out to equal the designed reaction. So in this case, since CH4 is a reactant rather than a product, so here it's a product, and in our parent equation it's a reactant. So what we have to do is we must rewrite the formation of CH4 as a decomposition reaction rather than a formation reaction. So we must flip the equation. So hopefully you can see that. Hopefully you can see this top equation. All we did down here is switch it around. When that happens, we also have to change the sign of the change in H. So because the formation of CH4 was a negative 75, to decompose CH4 it would be a positive 75. So then what I look at here is I say, okay, CO2 looks like it's a product in my parent equation. So my parent equation is up here. So it looks like it's a product in my parent equation, and it's also a product in my broken down equation. So I can keep that one. And then the same with water. Water's also a product. And then this also works because oxygen is a reactant there and there. So now I'm done, and I can start crossing out my equations algebraically. So now what we do is just plug in those numbers over there. And again, I'm multiplying by 2 because there's 2 moles of water. So now what I do is look at, I can pull down CH4 because nothing is going to cross it out. So again, nothing in the products can cancel out CH4, so I just bring it down. So I'm going to algebraically sum up these equations pretty much. I can cross out my carbons because treat this like an equal sign. That's one on the right side, there's one on the left side, those can cancel out. I can add my oxygens up to equal 2, which is good because that's what my parent equation equals. I can cancel out my hydrogens, my 2H2 and my 2H2 here, much like I did with my carbons. and then I can bring down my carbon dioxide in my water to show algebraically that the decomposition of CH4, the formation of carbon dioxide, and the formation of water all together can be brought to my parent equation, and that's my change in heat of the total reaction, which is negative 890.3 kilojoules. So this is Hess's law the long way, where we manipulate these equations. So essentially we've taken the three separate equations and we've made the compounds into the original equation and manipulated them again to show that final reaction and that final equation. So Hess's law, the short way, is just like what we did in the notes. We're going to use the change in H of the fusion and look at the products minus the reactants and just simply calculate. So it's a little bit faster, a little bit shorter. So we're going to show our work and put our products here, so carbon dioxide and 2 waters, minus the CH4 and the oxygen. So products minus reactants, and again, in order to get full points, you have to show your work there. And then we would just plug in the values, and we can calculate for the same change in heat of the reaction. So thus, Hess's law the short way. So then we're going to flip over the sheet and I will explain to you how to do some of the problems for Hess's law the short way, and then also kind of explain just step by step how to do one problem and all the expectations for Hess's law the long way and the short way.